Hey, you wonderful physics kids. We're doing a lab. This is the third lab, actually. This is acceleration due to gravity. All right? You can pick it up as a PDF file in Schoology. It's sitting there for you. And the purpose of this lab is to show how errors inherent in measurements limit accuracy and also using formula to solve problems. You get some practice with that. All right, so this lab simply consists of 4 things to measure acceleration due to gravity. Now we know acceleration due to gravity is going to be 9.81 meters per second squared if you get it right. So let's see what happens with different measuring activities and see how right we get it. So I'm going to do these here. If you would like, you may do this at home. If you could find a way to measure in meters the height of various things and drop balls from that. You could try to practice acceleration due to gravity too, but frankly, if you get the data from me and work out how to solve it, you're getting pretty much everything I really intend you to get here. So the first thing we're going to do is a 1 meter high ball drop, all right? So let's see if we can get this on camera here, all right? So I have a meter stick and a ball here, and I'm going to simply drop the ball and take the time. I have a little timer here, and I'll let you know what the time is. All right? So we are ready. We are set. 3, 2. You can take the time too if you'd like and get your very own numbers. I like it when you do that. You all have a stopwatch with your phone. I'll wait a second. You got it? All right. I'm going to drop this. I'll give you the time, and you can do the calculation for what this is with my time or your time. Ready, set, go. All right. All right. I got 0.30 seconds. So take that one down, 0.30 seconds. The next activity, I've already done this, so I don't have to take your time, is to find a higher spot to drop from. So I dropped it from the ceiling, all right? And the ceiling is 3.03 meters high. The ceiling is 3.03 meters high. That's 3 centimeters more than 1 meter. And it took 0.61 seconds for the ball to drop from there. 0.61 seconds. So you could put that into the calculations. So the first one is 1.00 meters. I dropped it from right there. 1.00 meters takes 0.30 seconds. The next one, 3.03 meters, took 0.61 seconds. The next one, well, this one is exciting. We go into the hallway and we drop the ball. All right, there's the ball. Okay. We go into the hallway. We go up to the top of the steps. We wait till somebody's coming. No, we don't wait till somebody's coming. We make sure the coast is clear. And then we drop the ball from the top of the stairway down. Well, let me see what we get here. The top of the stairway, we measured it to be 5.33 meters in height. And you want to come out and watch me drop the ball? Ooh, come on. Come on, it's like a field trip here. You haven't been in school forever, right? All right, do I got the stopwatch? Hang on a second. I got to get the stopwatch. All right, where's the stopwatch? All right, so I got the stuff. Shh, don't tell anybody. All right, we've got to do this fast. It's physics on the fly. All right, so here's the stairwell. Currently unoccupied. That's handy. I'm going to show you where the ball is going to land, I hope. Yeah, right there. I'll let you know when I'm gonna drop it, all right? I'm running up to the top of the steps now. 5.33 meters. Ready? 3, 2, 1. All right. Didn't hit anybody. I can even be here without a mask. Shh. It took 1.16 seconds for that to hit the ground. Is that what you got? 1.16 seconds. All right. We got one more timing we got to do. Now, we've all used a timer for each of these three. What do you know about humans and their ability to start and stop a stopwatch with any consistency? What do you know about that? Are we good? We're not so good. We're not so good. We're not so good. Do the calculations on those three things. Find out what you're finding the acceleration due to gravity is on each of those situations. You're probably going to find we didn't do so well. Once in a while we get lucky, but mostly we don't do so well. If the numbers are working out well, they don't always, but if they're working out well, what you'll find with a 1 meter ball drop, we're so far off, it's ridiculous. Why? Well, I don't think your fingers are any good at starting and stopping a stopwatch to within about 1/10 of a second. We're about that bad. Well, this was, a 1/10 of a second is a huge amount of the time it actually took to fall, which means you could be off by such a tremendous amount with just 1/10 of a second off. The higher ball drop took a little bit longer, so 1/10 of a second is a smaller part of that total time, so theoretically at least, we shouldn't be as far off. Now with a 5 meter ball drop, again, 1/10 of a second is a much smaller amount of time, so we should be getting closer, theoretically. But there's other things that could go wrong with this. We're focused on the time, but you could start it at the wrong time as well as stop it at the wrong time. And these things add up. So how do we deal with this? Well, the best thing in the world is to get people out of the equation entirely. And how do we do that? Well, you're not going to be able to, but you can get them out of the equation as much as you can. Here's the deal. What we have is an electronic timer. Let's measure the height of this above the pad that stops it. All right? Come here. Look at this. All right, look at that. All right, so I have to put, to show you this ball, when I release it, it starts a timer. When the ball hits this pad down here, this pad down here, it stops the timer. So I have nothing to do with anything. All I do is release the ball, and it's electronically timed and will start and stop automatically. What I have to do, though, a little human error here possible, is I have to measure the distance. And if I measure the distance carefully, look at that. I have exactly 89 centimeters. Exactly. Well, what does exactly mean? Do we ever have an exact thing? So, as far as I can see, it's 89.0 centimeters, which means it's 0.890 meters for the ball to drop. Let's do this and see what time we get. All right? Are you ready? If this works, this should give us a pretty accurate time. So we'll see. All right? I got this reset. And 3, 2, 1. Nice. Okay. I've taken this time before, and it seems like the time is good and consistent. And that time is 0.426 seconds. Again, 0.426 seconds. The height was 0.890 meters. See what you come out with the acceleration due to gravity and that one. You should do a lot better, all right? Hopefully. So there's some questions on the back. Should we go over those a little bit? Why don't we go over those just a little bit, okay? What was the limitation on each experiment? In other words, what factor kept most of the attempts from being accurate? I don't think I gotta spell that one out anymore. That's me, right? I am defective because I'm a human. My nerve signals don't travel so fast. So I'm not gonna be a good timer. I might be good at a lot of things, but timing, not good in terms of physics stuff. Okay, you know the acceleration due to gravity. What's the percent error for each experiment? Remember what that percent error formula is? I put it on the sheet for you. Difference from accepted value. So find out how far you are from your 9.81 meters per second squared. Divide that by your accepted value, your 9.81 meters per second squared, and then just multiply by 100. Toss a percent sign on at the end. Don't use the percent on the calculator. That'll mess you up. But just multiply by 100, toss a percent sign on the end. That's your percent error. All right? So when you look at these, see what you find. Are we doing better? Do we have a smaller percent error as we get higher? Theoretically, we should. See if it works. Why did we find a high spot to drop from? I think I explained that. Rewind, you'll see. And did it help to go higher? Well, you tell me. Theoretically, though, if we, I'm sorry. Forget theoretically. Actually, if we go up, say, a couple hundred meters up in the air, we drop the ball from up there. Now, is that going to give us a tremendously good time? Or does that, when we actually go to do it, does that induce some other errors? Think about what some other errors are that going up 100, 500, maybe 500 meters up in the air. What errors might that induce? You know the physical world. What errors would that induce that would cause you to not get a good result? Think about it. Tell me something. And why did this last experiment nail it? All right. Should you say you got rid of all human error? I'm standing here. Should you say that? I had something to do with the experiment. So certainly with humans conducting it, there's a little bit of potential human error. But what did we remove? It should give you very good results. Well, that's the lab. Hope you enjoyed it. And yeah, this is acceleration due to gravity. You know what it is. Doing the formulas, a little bit challenging. Make sure you do them properly. By the way, Given's formula, S and S, is the shortcut to getting right answers. It's not a longer way around, people. And you already got it. You knew what I was going to say. You people are wonderful. When I said and, you all went, he's going to say units, isn't he? Yes, units. Remember, without the units, please go down the hallway because you're not doing physics. Thanks. This is challenging stuff to get you all to do it. But from the work I've been seeing, you guys are doing pretty good. For only 2 days a week, I am very impressed. Keep it up and know that when this is all done, hopefully you'll take some good physics away from all of this with you because it's really worth it. When you hit college, all these things I'm telling you, they will be a lot more strict, probably a lot less smiley with. So take them to heart. When you're doing problems, even side calculations, if you're not using units, it's not good. That's not good. It's not the way you should be thinking about it. All right? Keep on physicsing. Bye-bye, guys.